This week is kind of a, oh, you brought me fruit. Oh, last fruit cup's probably been there since before break. All right, so welcome back from break. Most of you hopefully had something exciting, nor not. So, or you suddenly woke up and you went, holy crap, it's Monday and I got to go back to school, and how did this happen? But we want to talk about databases. So for some of you, you're in database class right now. I know they occur the same semester, and just due to how people go through the classes, it ends up being they're in database at the same time. So some of this is going to be a really recent review. Every one of you before you graduate will have had a database class, at least in some sense. So some of this is an overview. But we're going to look at it more from the system, so kind of an overarching side. We are not going to make you build a database in here. We should have. Maybe that should have been an assignment. But what we want to talk about is kind of that overarching, how am I going to utilize this? Because everything we do in systems is really based around the idea of having that database as our core. So we're going to look at, there it goes finally. Computer's being a little slow. So we know a lot of these terms, and so now you've had them enough. So if you see the word DB, you go, yep, database, got it. It's some kind of pile of information, and it's generally, we think about it being indexed or somehow it's organized so that we can get to it. And we know that DBMS is that management system. We know there's a ton of them out there. And in fact, our discussion board has you looking at an alternative system, but we know that there's a lot of them out there. You can get Postgre, you can get an Advantage database server, you can do Microsoft SQL, you can do all different kinds of them. And that's that management system. And so that's how we control and manage that data. It's that software layer that does it. And then we have that idea of something called a schema. And that's really how this data is also. It's our organizational layout. And so if you want to think about it some way, it's how do we store the data, what are in the different fields, what are the limits on the fields, what are the constraints, and all those different pieces. And that we call our schema. And then we have this thing called SQL. And most of the databases we're going to work with are SQL databases. Now, what I love is it says the standard query language, and it is, but every implementation has its own little quirks from one language to the other. So you have to work with a little bit of the syntax. Some will require slightly different key codes or words, or maybe they'll have a colon where another one doesn't. So they all have their own little variances, but they're pretty similar. So if we do a select query, we know that it does something similar in all of the different languages. Just how it's laid out may be a little different. So it's kind of like English. English is great. We all think it's the same thing, but if you ever actually go to England, it sounds a little different. So similar type of thing. So this is kind of a very typical layout of what a database might look like. So your management system sits here and says, all right, I have all these, I have an administration interface, I have processing, and then we have to actually store it somewhere. And so here's where we actually store all that data, and we have the drive representations. And then we have different pieces. So maybe we have a program that interacts with it, because a lot of times our database on the back end does a lot of great things, but we have to have a program that then interacts with it and gets our information. So on the back end of your database for the database that you have in your student information system, there's a SQL database back there, and then a program sits in front of it, a web-based program in your case, and that actually interfaces with that database and looks at those rules. So, but you could also have people that have direct access. So if I go over into the admin building and I go to the computer services department, they have people that have direct access. They're allowed to run queries on that big pool of data. And in fact, there's a couple of different pools of data because they actually do a data mart and actually pull off the data every day and store it for database, and so we can do some data mining and do some looking at it. So what's all in this schema? So there's tons of stuff in a schema. So if I create a schema for my vacation, that's my plans for that vacation. Well, that's a database schema is really that same thing we've looked at. So it lists things like our tables. How do we have things broken down in our tables? How are those tables related to each other? How does that relationship work? And what about things like my individual data items inside of those tables? How many characters do I have? What kind of information can I store? What items are in that list? What other things do I have, including things like dependencies or constraints or security considerations? All that's written up in that database schema. That tells us how we build the database, how we do everything. It contains everything except the data itself. So it really details how and why and what we're going to have. So, a couple of things we know about our databases, or at least we hope when we build them. We know that with the appropriate resources, we can get direct access to that data. So we can run SQL queries. If you're the administrator, you can run queries. We also know that we need to have that access to be usable by more than one person. So think about Amazon. They have a database in the background, and if the only way that database could be accessed is by one person at a time, you could have one shopper online, it's not going to be very usable. So we have to be able to come up with some ways where we can have multiple users all in at the same time. So a lot of times these databases get much bigger than we're going to put on a single computer or a single server. And so we have to have a way that we can integrate those across multiple servers, in often cases multiple locations. So Amazon doesn't have their database stored in one location only on one server. It's got to be located on multiple servers, multiple locations. And so it grows past that, what we could use for, say, Microsoft Access. So Access is a great prototyping tool to show what a database might look like, but we need to think about it in terms of a much bigger, broader area. So we also have to think about what's existing in our company. So if I go into our company and they have a DB2 database, does it make sense for me then to go, well, for this project we need a Microsoft SQL database, and we have to pay additional licensing, and we have to then have our DBAs have to know both the syntax for DB2 and for Microsoft SQL. So we need to think about that. How do we integrate what we have existing? How do we expand it? And there are platforms that have reached their end of life, and that we have to think about, how do I then migrate from maybe a Borland Paradox database to a newer system? And I actually ran into that not too long ago. We need to think about that, and then we need to think about what our existing database is. If it's really just one desktop and a single copy, that's a different environment than if it's a very large globally based database that has multiple servers, multiple sites, thousands of users an hour interacting with it. So we have to think about that scalability and what that product is. And when we bring new components in, how do I start integrating them, especially on a very large database, so that we don't create issues? And then we look at our existing plan. So remember that in most systems, most business-based systems, that database is that core. So when I change that design or add to that design, I really need to think about what that's going to happen to other systems and other portions of my company. So maybe I'm integrating something in the accounting and the billing department. How is that going to affect human resources if they're all using the same system? Are there pieces that should be tied together? Very possible, but are there pieces that may impact it? And so I need to think about those cases of what's going to happen. So there's some terms you may run into, and these are not universal. Some companies use different terms. Some organizations use different terms. And so you may see that in this case of somebody who's called a data administrator, So in this case, we say they have the role of structure and integrity. So in other words, they design a lot of things. They come up with the standards. How are we going to do things like name conventions? And I know that sounds silly, but a naming convention where we use underscores versus we use camel case, if we're not all at the same standards in our company, it can really make it a heart attack for somebody coming in because they don't see what a name is, or they may not see it. So this person's also generally in charge of, in a conventional structure, things like who owns the data. Well, what do you mean by who owns the data? Who owns the maintenance on that data? Who owns the confidentiality? In other words, who sets what pieces of data can be viewed by other people? Here at Peru, we have a lot of data that we can't reveal. You can't go in and look at somebody else's grades, obviously. We also have financial aid information where we still have to tie back to things like Social Security numbers. How do we redact that so that as an instructor, I can go in and look at your grades, but I can't see your financial aid information, so those kinds of things. And then a lot of times they're tasked with the idea of data quality. In other words, keeping all that information that's coming in and out valid. So through sets of rules, making sure that we do complete transactions, making sure that we don't have anything odd in that data, that it comes in and it's intact. So we want to make sure that all that data is useful. We want to make sure it's intact. So the other person you'll see a lot of times is somebody called a DBA. Now, some organizations, they call everybody that touches a database a DBA, database administrator. So these roles sometimes can overlap. So if I think about it in this way, a DBA is more involved than in the day-to-day operations. So things like, how do I transform my database slightly or change queries just a little bit so that they run faster? Maintenance operations. So they may do things like backup and data recovery. So a lot of times, though, these roles get mingled. And in a lot of corporations, they're all the same title. They all have the same area. But so these are the people that actually work with the data. They're not inputting the data necessarily, but they're the ones that manage and maintain and try to make sure that it runs as smoothly as possible. And sometimes these performance tweaks, little changes in queries. So those queries that live behind the web interface that you don't see, how we order them can sometimes be dramatically different. And so a lot of cases they're trying to maintain and make sure that this runs as fast and as smoothly as possible. And as the size of that database scales up and as the number of users scales up, that becomes more and more important. These databases, I can almost think of them as a living system because they do change over time, and we do need to keep them moving and making sure that we have that. So this overview might make more sense. So here we have that data administrator, so they're kind of the standards of it, and then that DBA is the one that actually does a lot of these pieces, including that idea in a lot of cases of security. This is day-to-day security, trying to maintain it. This sets the standards for that security, and so that's kind of the difference. And no, as a DBA, nor do you have to have the cheesy mustache that they have in the picture, or do you have to wear the really bad suit jacket that doesn't match your pants. You can dress normally. And DBAs are a great job, and so are data administrators. Usually, you work up in a corporation. At first, you may be doing DBA, low-level stuff. You may be doing one task. You get more and more skilled and more versed, and you do more certificates. Maybe you do more training. And then eventually, you move up into that administrative area where then you're tasked more with the control and procedures than you are with the actual data itself. So this should really be a review for most of you. If it's not, then you're really out of sequence, which is fine. Sometimes that happens. But we want to talk about what a relational database is. And so that database is really nothing more than groups of tables. And those tables have relations with another table. And those tables then tend to have columns and they have rows. And so it looks like an Excel spreadsheet. And in those, we have a single cell or a table where a row and a column intersect, and that holds one piece of information. One piece of information. In the background, though, we also store metadata about that in terms of what size and what type of information and what can be stored in there. So it's a little different than Excel in that regards, but if you want to think about it as terms of those XY tables, you can do that. So we also have to think about how they connect with each other. And the benefit to these tables is we can start to pull data apart and eliminate redundancy. And so for us to be able to put things back together, we have to have a set of keys that link these tables together. And so a primary key, every table will generally have a primary key. And that primary key, what is in that primary key, in that cell or that attribute, is unique. So if I think about students, and I have a table of student names, I may put something that's unique. I may put a unique identifier, like your NUID. And that NUID is unique for every row that's in there. So if I identify a single number in an NUID, I can identify a number or a row. There cannot be any duplication. That's part of the system, how we've built this. So the primary key then represents a row in a table. So if I represent an NUID, it represents a single row. A foreign key then is in another table. And a foreign key is in a different table. And that's how we match those items together, is we match a primary key with a foreign key. So maybe I have another table, and that table happens to have information about students who are athletes. And the primary key on that one may be a different value completely. So it could be your athletic number. Maybe they've assigned you an athletic number here for accounting purposes. But in that table, there is also a foreign key. And that foreign key would have your NUID. Bless you. So we match them together. And one of the big keys in this is, one of the big items in here is that foreign key can occur more than once. So in that second table, I could have multiple copies of that NUID that you used before. So think about a great example we use all the time in the database class is that idea of classes. In that class list that you take every year, you hopefully take more than one class a semester. If you're only taking one class a semester, you're on the extended plan to get your degree. So the primary key, your NUID in the list of students, matches up in that list of classes taken multiple times. And so I can create that link between the two of them. And so if I look at an actual table, it might make some more sense. So here we have one table out of a relational database of some point. And so one field here, in this case, they have the description, they have a gender, they have a product ID, and that product ID happens to be a primary key. So it's not duplicated in this table anywhere. If I put in the key phrase 1245, I know that it's a male fleece crewneck sweatshirt from supplier West Coast, manufactured by Adidas, etc. So I get that piece right there in there. And so the other term, though, and this is one of the cool terms, and for whatever reason, I've always liked this term, one row is also called a tuple. I don't know why. It always just sounds interesting to call it a tuple. So one row, one record, whatever you want to call it, and then we have a column. So we then have to figure out how we can put two of these together. So this should look really familiar to some of our diagrams we've done earlier, where now we have two tables. So we have table product item, and we have table inventory item, and we have a relationship between these two. So we know that we have to have a product item, and we can have 0 to many, or an unlimited number, however you want to phrase it, of inventory items. And so we have that relationship between those two tables. And then when I look at it this way, so notice now that product ID, I can have a primary key here, and then down here, multiple hits of that, because now it's a foreign key in another table. So that's how we can then join these together. And we can start looking at how do we get these pieces together. So if I look at our RMO, and this is a list of all their classes, well, now we can start to build and start to look at, hey, there might be a way we can put this and convert those into tables in our database. Because we've done the hard work now. We've broken most of this apart, and we've said, all right, so now we have an inventory item, we have a product item, we have a sale item, we have all these different tables we've already got ready to go. This looks a lot like that relationship view in Access, if you ever look at it. And so based on that, we can create a set of tables. So here's our initial set of tables. So we have things like cart item, and we put what attributes we need in each item, or what we think to start with that we need in each table. So we've taken our business problem, we've broken it down now into some tables, it looks like, and now we've figured out we need these tables, and these tables have these attributes. So we're in that design stage of trying to break it out. Well, now we've taken that same list and we said, all right, what can we use as primary keys? So we had to look for what they call candidate keys, or things that could be a primary key. And in some cases, we may need to use multiple keys, or we may need to add a field in here once we come in through. So now we've said, all right, we know that accessory package, we need accessory package ID. All right, so if I look back here, did I have accessory package ID? No. So I need to, in some cases, add something to stand in then as that primary key. So, and you'll see that we've had to do that on several of those. We've had to add in some kind of an ID. So sale item ID, sale ID. So those are all primary keys. So when we start writing that diagram or that description or our thought process, we know that those have to be unique in our system. So one of the problems we have, and you've probably talked a lot about it in the database class, is the idea of I can do a one-to-many, because I can say I can have one primary key relating to multiple foreign keys. But we run into a problem when I have that many-to-many relationship. So if I think here at our college, I can think of, I have many students who take many classes. But I have a problem when I actually do the database with that. Because I know that primary key has to be unique, it can't be a many. So I almost always have to break those up by adding a table in between there. So I have students, I have classes. In between, I have to have some kind of a junction table, some way to break up that many-to-many relationship. Because I can deal with a one-to-one, I can deal with a one-to-many, I can't deal with a many-to-many directly. I have to bring in another table. So you'll see things like sales transaction, class transactions, all those different kinds of tables added in there. And so that's what we're looking at when we break them up that way. And we'll see a better example of it. So now we've added all these keys. So we said, here's our foreign keys. We've added them in. And so now we think we can actually create a table structure that's going to work for us. And then sometimes we have to create, this is what that many-to-many was talking about. We add these association keys, is what our book likes to call them. There's a ton of other ones we can call them. But what it does is we actually take two items, a product key from one item and a product key from the other table, and in a lot of cases we use a concatenated key. In other words, the key comes from two different tables. So a great example of that is this promo offering. So promo offering, the product key, the primary key here is both promotion ID and product ID together. It's not one by itself because that comes out of this promotion table, and it's not product ID because that one comes from there, but we know that we have many promotions with many products, and so we're trying to break that into a table in between the two of them. And that's one of the hardest things to kind of wrap your head around when you're designing those databases, is to do that. So then our final table list is a little different. It's got some additional pieces in it. And so in fact it takes two different sheets here so we can look at it. And so we have to have some way to put all of those pieces together. And then we can have a database table that will look and function effectively. So, a couple of other things that we need in here. And we have this idea of something called a constraint. So a constraint is just a rule that does something. And so we need something called referential integrity, so that we know that the foreign key and the primary keys relate to each other, bless you. And we know that the rules about those are effective, that we have one primary key and you could have multiple foreign keys. And so if we put a constraint in there, we can put that right into our database that we know that rule has to exist. And so that's what we're looking at with that. We can put in a lot of other types of constraints, but that's one of the big ones we have to start with, that idea that we have to have a primary key and we have to have a foreign key. And they have to adhere to our rules for that to be valid. So here is where it gets ugly, or uglier. And this is probably, I think this is the hardest concept as a student to wrap your head around, not having built databases and started to pull them apart. And that's that idea of normalization. So normalization is a technique where we break tables off to get to the point where we have some rules about it, but really the essential part is we want each table to not depend, all the items in that table depend only on the primary key. And so there's three basic forms. So there's first, second, and third normal. And ideally, we would get our tables to third normal form. And we think that's the kind of the level where we can get things to function most effectively. There are additional forms. There's a Boyce-Codd normal. There's some other ones that exist in terms of how do we normalize our database. There are times we actually take a normalized database and we actually break it down a little bit and go downwards for improved functionality. And so it's probably a little outside of the scale of this, but what we're looking at is first normal says a table is in first normal form if every field contains only one value. Okay, so every field contains only one value. So we have items in here. So notice up here at this top one where it says dependents. And dependents, it just made a list of John, Alice, and Dave. Well, that doesn't work very well for us because we have to somehow parse out, does that really mean that it's the guy's name is John, Alice, David? How do we deal with that? And that may work really well, but we've broken it down into this, and we said, okay, so we have a dependent, we have a dependent, we have a dependent. Anybody see a real quick problem with that right away? What's the problem with that right now? So we're in first normal. We've got it to first normal. What's going to happen then? How do we know how many dependents you have? Do we just artificially limit you to 3 dependents? That's all you can have. Justin, when you get married and have children, you can only have 3, because our form says you can only have 3. Justin says, I don't want even 3. Nice. Nice. But it limits us. It puts some constraints on what we can put in there. So typically, what we do is we move those, and we say, all right, well, dependents then we're going to move. So we saw those multi-valued attributes, and we move those off into their own table. And so now we have a list of dependents, and we tie them. So notice that Social Security number is the primary key. Here, Social Security number is the secondary key. And so I can look up whatever the 3333 Social Security number is, and I can quickly go, oh, yep, that belongs to John, belongs to Alice, belongs to Dave. And so you could, in theory, have an unlimited number of attributes. We've all got that one weird uncle who has 17 children with 4 wives, right? Maybe it's just my family. Okay, never mind that. But they don't. They don't. Because it's a primary key up here. So Social Security number is the primary key in the first table. And so it's unique. When I say 111223333, that refers only to Mary Smith, accounting, and her salary. But it's used as a foreign key here. So the record ID is the primary key, so it's unique, but the foreign key can occur multiple times. So if Mary Smith had 17 children, she's going to have 17 dependents listed in there. So that's how we can break those up a little bit in that first normal form. All right, so this is where it starts to go off the rails a little bit for some people. So we need to figure out about something called functional dependency. So attribute B is functionally dependent on attribute A. If each value of A, there is only one and only one value. All right, that sounds horrible. But the reality is we can look at something like this. So that product ID is dependent on supplier ID. But that supplier is not dependent on our product ID. Does that make sense? It's a one-way function if you want to think about it that way. So our product ID, when we create item 1244, every piece of that needs to be dependent on that ID. So it's West Coast and it's item 1244. But that supplier, notice that supplier can happen several different times. So it's not dependent only on a single product ID, if you want to look at it that way. So we have to kind of break these down in that functional dependency. So the other piece that kind of comes into mind here then is, can I get casual chino trousers from a different supplier? Yeah. And in fact, could I probably buy Adidas trousers from a different supplier? Yes. But I would use a different product ID then for those. So we can create these dependencies. So that's kind of one of the harder ones until you've started doing with them. So that's where it gets a little tougher. So we also have to say a table's in second normal form if it is in first normal form. So you have to go through the list first, and each non-key attribute is only dependent on the entire primary key. So that's our second normal form. So in this case, we have a couple of things that we want to look at. So we have regular price, we have promo price, and we're in a table called promo offering. So the key for this is promo ID. Does promo price, is it dependent on the promo ID? Yes. But is the regular price dependent on this promotion? No. And so in that case then, we'll just take the regular price out of this particular table to put it in 2NF. So third normal form then. Third normal form, we have to be in first, and then we have to go to second, because second says I have to be in first, and then we get to third. And so our third normal form says no non-key attribute is functionally dependent on any other non-key attribute. All right. So let's look and see what that actually looks like, because sometimes it's easier to look at one here. So if I look at this and I say, all right, so here's a table. It's got sale price, shipping tax, item total, and total amount. So we have to think about where those items come from. So it violates third NF. Okay. Shipping plus tax plus item total equals total amount. So if I know that, do I need to have this column exist at all? If I can create it, essentially, without having it in there explicitly, do I need to have it in there? So in other words, I have to have shipping, I have to have tax, I have to have item total. So I add all three of those up, I get total amount. But do I need total amount actually right in that database? No, it's dependent not on the sale ID, it's dependent on those individual items. And so that's where it becomes an issue. And this is one that sometimes we violate, though, because what can happen, or what we may want to have happen, is if it takes a long time to process and we do it repeatedly, we may put this in just to have it in there. And so we would say, all right, I know that third normal form says we shouldn't have that amount in there, but we find that that table runs faster, or our process runs faster, by having it in there. And so that's one of the things all the books say, you know, you have to do these steps. Sometimes the reality is we pull back a little bit from that, because it takes that computer just a little bit of time to calculate 850 plus 9135 equals 9935. Now, if I'm just doing one calculation, you're not going to notice it. But if I'm Amazon and I'm calculating it out, you know, hundreds of thousands of records a day, it may be that we leave that in kind of a 2NF form, and we do that. So the other solution, if we can't just get rid of it, is we can actually make a new table so we can get rid of that information. So here they had a credit category, and in this case they moved it to a credit rule, and so here's a credit category based on a credit rating. And so you can see, depending on, as that gets bigger, whatever credit rating they generate, it changes that. And so you can also get rid of your duplication that way by pulling it out of there. So we end up with a lot of tables, unfortunately. And then we need to be able to put them back together. And you think, well, man, that seems, why don't we just have one giant table with all this information in it? Wouldn't that be easier? The reality is no. And if I think about you here as students, and I have a giant table, and it listed every class you took and all your information. So it would be Connor and your hometown, and your database, and all this information about you and the class you took. And then it would duplicate that over and over and over for every class you took. And some people take a lot of classes before they graduate. You should take about, 40 classes or so to graduate? Some people take a lot more than that. So we would have all this duplicated data. And so the goal of this is to get rid of that duplicated data. So as we look at this, we come up with a couple of different pieces. And so one of those is we need to figure out what kind of data we're storing. So data types, or what kind of data we store, is dependent on the database system we're using. Different database systems allow different types of data, and different sizes of data, different lengths if you're talking about characters, or if you're storing things like images or other data, it's going to store different type. And so some fairly standard ones Standard ones, we have things like integers, small integers, big integers. So whole numbers, essentially. We have float numbers. In other words, they have decimals. A lot of databases have money or some kind of currency built in. And then they have, in this case, they call them inchar. So you have a length of characters that you can do. So in Access, for example, when you worked at it, the most common thing if you did a character string was you could have that character string be 256 characters long by default. Well, when I do that, it stores 256 characters. But if all I'm trying to get is somebody's name, do I need all 256 characters? Probably not. And so if I make that smaller and I manipulate it to the size I want, I'm better off. So there are other ones that have variable length sequences, and so it depends on which language you're using or which SQL version. And then we have XML, which is kind of moving in. And in fact, in some cases, we can store significantly larger values in a single pool than that. But a lot of times date and time, and so it really depends, though, on what system you're using and what you're looking at there. So we need to figure out what our data types are. You want to minimize those, and that's part of that structure when you create that schema. If you create a 512 character limit for a name, hopefully nobody has a name that long, because that would be really horrible when they're in grade school. But we want to make it appropriate. If you limit it to 10 characters, well, then you have a different issue. So I have a retirement account with a company who it drives me crazy every time I log into their system, because my login name, they limit it to 8 characters, which is, from a security standpoint, has some issues. And I can't remember what I've shortened my, first name, last name combination and all these things to get in the 8 characters. So it's, I think, an issue. And now at this point, because they're an older company, my guess is that limit is based on a system they had at some point in the past, and they have a hard time coming up with a solution to that now. So a couple of different terms you may run into. So a decentralized database. So we don't do a lot of sales. Maybe this is only for reference. And so the example on a decentralized I've seen used is that of a auto mechanic buying something like ALLDATA CDs. So that CD loads and it installs a database on their computer, and they can look up parts and they can look up how to fix something. But those databases don't necessarily need to be connected in any way. There's no synchronization needed for those. Homogeneous, though, so they're stored at multiple locations. Multiple locations, they're all using the same database management system. So State Farm, for example, they have multiple locations, they all need to connect, and they have a coordinated global schema. Heterogeneous, though, says, well, our database is stored at multiple locations, and we may use even different database management systems, different schemas. So we have one big pool of data we think we need. It's stored in different places, and we use it all differently. So that's really a case of something like our MyPSC system. So MyPSC, in this case, we do actually all use the same database management system, but we all have different schemas. UNL's schema is different than Peru's versus Wayne's versus Kearney's versus the Med Center. They're all different schemas, and they all take that data and look at it differently. In fact, they've created that data differently, which has been kind of a sad thing in some ways, because we would have thought that we would have said, all the state and colleges in the state, universities, would have come up with a single cohesive plan. You could log into MyPSC, you could enroll seamlessly in a course at UNL and transfer it in. And that isn't the case, because we all have different pieces we wanted, and nobody wanted to give up the turf and have a globally coordinated schema. So we have multiple schemas, and so you may find that even though we're all using the same back-end piece, all the same pools, it's much different at UNL than it is at Peru, for example. And certainly we see that quite a bit. And so you'll see that we have those broken down. So this is just a picture of an idea. So here we have our global schema, and we all coordinate through, and the data is stored at multiple locations. So a really great example of that would be something like Google, if you want to look at it. Google doesn't care which one of their distributed database systems you interact with, because it's all coordinated and all sent back through the same system. So, and then this is more an example of what we have at Peru, because we do have different types of local and different schemas. So there's some global schema in cases of things like the NUID and a few of the tables in terms of information. But when we get to the college and the class levels, it's all done individually, and so it's all different, which, again, there would have been some great utility in that. So how do we do it? So how do I synchronize all these remote sites? So I have different places, different pieces. How do I start to synchronize those? And so there are a lot of different ways. It depends on how we're going to do it. So replication says each site has its own copy. And so, in fact, we do some of that. We don't have our own database based at Peru, but we do replicate the database that's stored at UNL to the one that's stored at the Med Center. So they are in synchronization. So every time we make a copy of an item at UNL, it sends it over to the Med Center, and those databases are synchronized. So if UNL, suddenly Lincoln has no power for a week and a half, but Omaha does, we can still use that database. All the data is there. It's all usable. In fact, it's a completely duplicated site. So we can also store our data in different locations. And so for a lot of companies, this makes sense. So in this case, we're storing pieces of tables at different accounts. So it's the same table. So here we have account number being the primary key, last name, first name. But based on where they're located, we store pieces in different areas. So banks will do this because they don't need to store all the information for all the Chinese customers when they're also having a US-based bank. And so they can split that data that way. So that's a horizontal partition. You might have a vertical partition, so where you're storing different columns in different locations. And so it may be that, again, in this case, we based things based on US and Japan, so we looked at it from countryside. But even here in the US, you may have multiple data sites, and you may have different needs. So you may have a call center in Maine and a distribution center in Kansas City and a manufacturing plant in Arizona. And so you may need to split them up based on either vertical or horizontal partitions, depending on that data. And so then once you do that, you do need to send those updated, replicated pieces back and forth. So here we have one that's partitioned out, and then it's replicated. So we can see how that would work kind of on a bigger scale. And so there they have warehouse land. They have 3 different locations in the warehouse. They have a data center, corporate headquarters. And so we have to then replicate all that data. And you never want your data to live in just one place. So when we talk about things like backup, we usually say, well, you need at least one backup, preferably 2 methods of backup. And the same way when I replicate my data. I don't want my data all just live in one house. Because if that house burns down, we're all in trouble, right? So how do we do that? So, a couple of other things we need to grab is that idea of logging. So in a database system, not Access obviously, but in a large database system, everything we do creates some kind of a log. So any transaction on the database, any change to the database structure itself creates a log. So it does 2 things. One, it's a way we can prevent fraud so that you can't do the Office Space trick of rounding off a penny and depositing it into your account, or at least we can find it if you do. But it also gives us a way to recover if we have a failure. So if a transaction doesn't complete, we can look at that log and say, oh, I see why, and we can roll that transaction back. If we implement changes to the system and they don't work, we have a way to roll that system back and go, ooh, you know, that change we made to try to process students faster didn't work. We can roll that back. And so in database class, you learned a lot about these different things called concurrency or controls. So concurrency is really that idea we need to be able to work with multiple users all at the same time. And so how we do that depends on the database system we have and how we want to do that. So one of the things we almost always do is we have what's called a transaction. So a transaction means every piece of that transaction goes through or it all gets rejected. So in other words, if I go to the bank and I put in a deposit and that check has to clear and there's several steps, all of that has to go through or it all gets rejected and they hand you back your check, essentially. So everything has to go through. So we generally call that kind of an all or nothing approach. So all of the transaction has to go through. Because think about it this way. What if you went to an ATM and you put in your card, you put in your PIN number, you said you wanted to deduct $200, and then the dispensing mechanism jammed up on that ATM. It takes it out of your account already, but you don't have your $200. Are you going to be happy? No. No. So in that case, it would roll the whole transaction back, and we would do that. So we also have concurrency issues. So when you're married, think about you and your wife hitting that ATM at the same time. How are we going to make sure that we get the correct amount deducted from your account? So we have different types of locks that we can use. So we can lock with either an entire table, we can lock a row, we can lock a column, we can lock an individual cell. The more complex the database system, the more complex of types of locks we can use in our database. Something like Access, really you can lock the entire database and say, nope, you can't get in there. Or at most you could lock an entire table. Well, that's not going to work. If you think about Amazon, they're not going to be able to lock an entire table of sale items just because you went, browsed, and threw it in your shopping cart. So we need some ways to deal with that a little more extensively. And so luckily, we're not going to go into that in great depth in here. But in your database class, we explore that a little more in terms of different types of locks and different types of errors that can occur. But just to kind of give you that piece, if you have a database and you don't have it properly done, you can run into some concurrency issues. You can run into an issue where a transaction partially processes, or a transaction processes and it doesn't post right to different tables because part of that table is locked or hasn't been locked in that case. So how we protect that database. We know we need to replicate it. We know we need to back it up. And those apply whether it's a single computer running Access or some other abomination, or whether it's a large-scale enterprise system running Microsoft SQL, for example. If it is a huge database, you will have those pieces in there. And you will also hopefully have people that understand those, and they're not going to have just a single class. So you're going to probably be on the overarching side of that, and you'll be looking at how do I design it versus how do I do the individual pieces. So that's kind of the database in a really quick nutshell. That is an entire semester's worth of class I just gave you in 45 minutes. Except I didn't make you do any of those, which is always the hard part of that. All right, so really quickly. So this week, your next part of your final project is due. And I've got about half of the people have actually responded. You had a phone or a Skype with them about their project. I've got a few who didn't, though I'm going to just go ahead and type out some comments and send to you so you can work on it from that point on. So part 3 then says, all right, you've looked at your technology, you know the business, you know a little bit about what their needs and wants are, you see what they're using already for existing technology, existing information systems, and now you're going to look at what can I do to utilize that better, the things they have. How can I gain an advantage by using the same things they had. And so my classic example is walking into a hospital, and they have up an Excel spreadsheet, and they're typing in numbers furiously into it. And they have rows and they have columns. And then I see them reach for a 10 key, and they use the 10 key to compute the sums. They didn't know how to utilize that technology they had. They thought it was just a place they could throw numbers. They didn't have any idea or didn't have the knowledge of how to set it up to actually add columns and add rows together. And so it's that idea of how can I change things that I have existing. So this also, it's kind of a gray area. There are sometimes things will fall into this and the next section. So if they have an older computer system, for example, maybe instead of saying, hey, new technology is this, but you notice it's only got 2 gigs of RAM and is really, really slow, hey, maybe a way to utilize what we have better is to spend $40 on eBay, buy some memory for it, and make that particular system faster. Or you have QuickBooks 2010, you're doing payroll on it, but you're having to hand calculate what they have for withdrawals from employees because you don't have the latest tax tables. You know, an upgrade to the latest version would give you that piece. So it's not new, it's just an upgrade or a modification of what they have. So there is some gray area in these particular items about which and how they apply. So if you have a question, you are always welcome to email me, and I will try to answer as quickly as possible. So ask questions. Say, hey, does this make sense as an upgrade, or should I put it in the next section of the paper as a new and a wonderful technology? And so we'll decide that. We can think about that. There's not a rule that says it has to be in A or it has to be in Part B. It may vary depending on the business. So some businesses may have, as part of their update plans, may have a regular rotation of computers. That's new technology, but if they're then installing Windows XP on it, maybe that's something we need to think about. Or if you think, hey, I see a printer, I see they're using a, genuine toner cartridges, and I happen to know that you can get the remans and they're not sending them out to customers, it's just for internal purposes. Maybe that's a better way to do business. But maybe an even better way would be to say, how can we do this paperlessly where you're just saving PDFs in a format? So this is really one where you have some judgment and discretion. So if you have questions, email me on those as quickly as possible, and I will try to answer as quickly as possible.